Okay. Recording also started.
You can start.
Okay, we can start. Ladies and gentlemen, good afternoon. And we are pleased to have you in this session monitoring. I have the honor to present you the chairman, who is Professor Meres Jamei, Professor of Soil Mechanics and Environmental Geotechnical Engineering at the National Engineering School of Tunis. And the discussion will be managed by Professor Nicola Casagli, full professor of engineering geology at the University of Florence. So, please, Professor Jamei, you can start.
Thank you, ladies and gentlemen. Good afternoon. It is with pleasure to share this session and to start with the interesting presentation about the monitoring, essentially, and analysis of some interesting cases of landslides. Each presentation, as you say, it is for 15 minutes long. We should respect this time. And I will do some short presentation of some of the authors. We have the first presentation, which is given by Conforto. I hope that my the noun it's okay. Yeah?
It's a hard surname, but it's quite okay.
Okay. Doctor from University of Florence, from Italy. The second will be by the Associate Professor Vassilo from Geotechnical Engineering University of Basilicata. Yeah. The third, unfortunately, will be not presented directly, but will be presented by recorded video. But there is I think Mr. Giuseppe Rusa, who is the PhD at the University of Degli Studi del Sannio from Italy, who will assure the discussion about their presentation. And also we have another which also will be at the afternoon will be also, the other presentation will be also provided by pre-recorded video. And the last for the first part is by Associate Professor of Geotechnical Engineering Damiana, who was, I think, in Tunisia. I remember at when we started the first conference in Tunisia about the landslides. She's from University of Campania, from Italy. Now you can start, Dr. Confiorto.
Thanks for the introduction. I'm going to share my presentation. So if you can give me feedback, please. Hopefully everyone is okay. Thanks. Okay. Thanks a lot. So today I'm going to present our activity here at the Department of Earth Science of the University of Florence. And first of all, I would like to start from motivation of our work. So there is this question I would like to show and to introduce, which is why it is nowadays possible to implement a continuous systematic monitoring of ground deformation at regional scale. Of course, I'm giving you also the answers. I mean, what I think these could be the right answers. And the first one is given by the thing that Sentinel-1, which is a Sentinel launched by the ESA, the European Space Agency, was specifically designed to acquire deformation data in continuous way over large territories, over large part of the Earth's surface. Of course, in parallel, there was a great innovation, a great advancement of INSAR technology. And the great progresses of the INSAR technology see Italy as one of the most important countries in the international panorama. Of course, in Italy, in some other nations of Europe, or even in the world, nationwide mapping projects are already implemented. There is also actually the EMGS, which is the European Ground Motion Services, which is starting now, and they will provide updated images of the Earth surface on the whole European continent. Of course, Sentinel-1 was fundamental for our project because of its configuration. Sentinel-1 is made by twin satellites, 1A and 1B. It acquires images, SAR images in C-band, which allows us to have a medium average resolution imagery. Of course, it's very important also the revised time of 6 days, which is one of the shortest, actually the shortest revisit time of the orbit. And this is very important to have continuous images of the Earth's surface. Indeed, thanks to this peculiarity, we can talk about monitoring project. In particular, we can say that we can implement monitoring project based on the PS continuous streaming at regional scale. In this slide, I wanted to make a comparison between the past and now. On the left, we can see that with previous missions such as Earth and EMSAT satellites, we could have had images with a revisit time of 35 days. Nowadays, with Sentinel, we can have images over a specific area every 6 days. This, of course, made let's say, a step forward from a static picture of the Earth toward let's say, a movie, a film, because, of course, many images overlapped create a movie. Starting from these assumptions, of course, we started several continuous monitoring projects at regional scale. First, we started with Tuscany region, which started this monitoring project in October 2016, and this benefits of about 2 million PS points. After that, Valle d'Aosta also implemented this kind of service in January 2018, relying on 700,000 PS points. Last but not least, also Veneto region implemented this service, started in July 2019, and in this case, Veneto region has information given by 3 million of PS points. Of course, these are the two main activities carried out in this monitoring project. Today, I'm going to talk about the PS monitoring, which is a service which is given to regional authorities. It's a service which is given in real time or quasi real time. I mean, we update every 12 days information about the deformation ongoing on these 3 regions. Aiming at providing an operational alert system, or let's say a continuous monitoring of the state of the displacement, the deformation occurring in the regional territories. The main assumption of the PS monitoring service is to identify the so-called anomalies. For anomaly is intended the variation of velocity identified by this delta V, which have to be higher than 10 millimeters per year in a recent time interval R, which in our cases in these 3 regions is set as to be 150 days. So we have a time series of displacement. We see if there is an acceleration and according to these parameters, and we identify these points as anomalies. To be clear, this is a short scheme, summarizing what I was saying before. So on the top, we have no anomalies. So we have points which have time series which are showing stable trends or linear trend of displacement. Of course, we can have anomalies whereas we have accelerating trends. So for instance, stable points showing acceleration, or points showing acceleration but experiencing an acceleration. Of course, we can also identify anomalies wherever we have a decelerating trend. Let's start from Tuscany. As I said before, Tuscany was the first one to implement this kind of service. Of course, Tuscany is varies from a physiographic and geomorphological point of view. We have more than 90,000 map landslides. We have several slides and complex landslides. We have also subsidence phenomena in Tuscany, as well as we have also some geothermal activity. Here are the Sentinel-1 data we had belonging to 2 different tracks in ascending mode and 2 different tracks in descending mode. And these are the anomalies we had in 1 year of this project, from September 2019 to September 2020. Of course, we have more than 5,000 anomalies. Most of these anomalies were classified, were interpreted by me and my colleagues as according to the triggering factor, and most of them can be classified as slope instability or subsidence. As we can see here, their distribution is different according to the physiographic context. For instance, we have most of the anomalies in Pistoia province as classified as slope instability, as well as we have in Prato province the majority of subsidence anomalies. Of course, in Tuscany, at the end of this, let's say, monitoring, at the end of the routine of this monitoring service, we deliver a monitoring bulletin to regional authorities in order to warn them about the ongoing deformation. In case of relevant and persistent, so let's say persistent anomalies in time and space in the same area, authorities are warned, and of course, in this case, additional investigation are carried out together with regional authorities. So every municipality which is classified as to be in class 4 has this kind of service. Then after, we can see also Valle d'Aosta region. Of course, in this region, we have mostly landslide due to the alpine setting of this region. We have about 2,200 landslides. We have also 150 GSDs. And of course, the landscape is glacial and periglacial. We have different landslides which are impacting the people and things on the surface. Of course, mostly are rockfalls or complex landslides. These are the Sentinel-1 data, 1 track in ascending and 1 track in descending. As we can see, they cover most of the region except for the higher peaks of the Alps. And these are the anomalies we collected in 1 year, in the same time span as we have seen before. We had more or less 3,000 anomalies. And of course, given the context, given the alpine settings of Valle d'Aosta region, we had almost exclusively slope instability anomalies detected. These are 2 relevant anomalies we classified. We detected and we delivered to the regional authorities. The one on the left is the so-called Bosmatto landslide. As we can see here by the time series of displacement, there was an acceleration experienced in the mid of 2018 with a delta velocity of 40 millimeters per year. And the other one on the right is the Comba-Dash landslide, which experienced in the second part of 2018 a DVEL of 15 millimeters per year. The last one, as I said, is Veneto region. Veneto is a very wide region of the northeast sector of Italian peninsula. In this case, we had more than 4,000 landslides, but we have also extended areas affected by subsidence, specifically in the Po Plain, and we have also a karst landscape. On the right here, we can see 2 of the main, let's say, landslides of Veneto region, the Tessina landslide and the Mount Rotolon landslides. These are the data we had, Sentinel-1 data we acquired on Veneto, the ascending and descending on the right. And here are the anomalies distribution on Veneto region. We had in this case more than 2,000 anomalies. And of course, also in this case, the anomalies were classified and their distribution is strongly dependent on the physiographic setting of the region. So we can see Belluno province, which is in the northernmost part of Veneto, has almost exclusively slope instability anomalies, while provinces like Venezia or Rovigo have only subsidence anomalies. A specific focus was carried out on the slope instability anomalies here, and we can see that the distribution of the slope angle of the anomalies is characterized by a very high slope angle. So every anomaly, most of the anomalies are distributed within the higher slope classes, as we can see here, and this is in agreement with the alpine setting of Veneto region, as well as most of the anomalies are in this case, comparing with the aspect angle map of the Veneto, are on the western faced mountains. So most of the anomalies are on western faced slope sectors. This is the case of a relevant anomaly in Veneto region. Is the one of Lamosano, which is a small village right in front of the Tessina landslide. As we can see here, the area is well known, affected by a landslide, in this case a landslide. Here it is what happened in December 2019. We had 3 different anomalies characterized by very high DVEL, as we can see here. So in this case, authorities were warned, and several investigations on the field were carried out. In this latest slide, instead, I would like to see what can be done next, what can be the next objective to implement, since the recurrent speed, revised time of the Sentinel-1 is the case of the Sich-1 landslide. So there is this Ximo landslide here, which is a rock avalanche that occurred on 23rd of June 2017. And as we can see by the time series, there was a strong pre-failure acceleration right before the major failure. By applying the inverse velocity algorithm, by applying the inverse velocity method by Fukuzono, a failure estimation, failure time prediction was possible, as we can see by the trend here shown. So summarizing, going to conclusion, of course, continuous monitoring allows to promptly detect anomalous movement, which can be interpreted and which can show a change in deformation trend, which deserve to be further investigated. These monitoring services are a real-time operational instrument, which have to be constantly updated, but can warn about potential critical situation. And this, of course, can provide useful indication for territorial planning and for risk management. Of course, the continuous acquisition of Sentinel-1 imagery, and specifically the revised time of 6 days, which is an unprecedented revisit time, may represent also a step forward for the prediction of natural events, as we have seen for the Ximo landslides. Thanks for the attention.
Thank you, Dr. Confiorto, for the nice presentation. Let's move to the segment, the other, by Roberto.
Okay.
You can start.
Yes. Thank you. Good afternoon. This work is the result of a collaboration between the geotechnical group at the University of Basilicata, myself, Jacopo De Rosa, and Professor Caterina Di Maio, and the electronic engineers at the National Research Council IREA Institute in Naples, Diego Reale, Simona Verde, and Gianfranco Fornaro. The study is based on the joint use of ground-based and remote sensing data for the monitoring of slope landslides. This is Varco Dizzo slope at the suburbs of the city of Potenza in southern Italy. It's the Basento River Valley, with the river running at the toe of a number of landslides occurring in the structurally complex clay formation of varicolored clays. From the view at the left, you can see the large number of boreholes drilled from 2005 on and equipped with inclinometers and the GPS stations. In this map, I'm showing permanent scatters visible from the interferometric processing of Cosmo SkyMed images. Scatters are present on buildings and are visible on buildings and roads. In particular, this is the National Road Basentana crossing the landslides. Let me also show you these two cross sections with an average ground inclination around 10 degrees, a length of the landslide bodies of the main earth flows around 1 kilometer. The former earth flow has a maximum slip surface depth detected by inclinometers around 40 meters depth, while the latter earth flow has multiple slip surfaces detected at about 20 and 35 meters depth. Let's start for ground-based displacements from the latter earth flow, which is Barcodizzo earth flow. Displacement rates are rather heterogeneously distributed on these landslides. Displacement rates are from 1 to several centimeters per year. Our monitoring starts in 2005, but there were previous investigations that started almost 30 years ago. You also see GPS data that in some cases helped for monitoring continuity when some inclinometers went out of use. As for the other earth flow, which is Costa dell'Agata earth flow, and that is slower, displacements in the last 16 years have been the results of seasonal variations of displacement rates overimposed to a roughly linear trend of displacements. Average rates strongly depend, in this case, on the position along the slope, and the rates are related one to another by a condition of substantially constant soil discharge. I'm also showing inclinometer profiles here for both landslides to stress the fact that displacements along the slip surface or the slip surfaces gives the main contribution to displacement, but there is also a contribution of internal deformations, so that it is not straightforward to put into relationship the shallow displacements, the ones that for a component are visible from satellite data, and the deep displacements. You need inclinometers to do that. Let's look at DINSAR data, so Cosmos SkyMed and NVSAT images separately for the two main earth flows. Besides the largest density of Cosmos SkyMed data, you can notice that the slope is mainly oriented north-south. This is the north. And therefore, also the prevailing displacement direction is north-south. And this, together with the fact that the slope is not intensely urbanized, makes it quite challenging to monitor it by the DINSAR methodology. I mean that just a small component of displacements is visible along the satellite line of sight. We identified a number of targets on buildings. Let's look at the loss displacements against time for some examples from Cosmos SkyMed data. They all result fundamentally linear, and there are different time series for a single building because several points are identified onto them. We're also seeing here the statistical distribution of loss displacement rates for these buildings. They go from a few millimeters per year to 10 millimeters per year. And I repeat, they represent just a small component of the displacement rates. We obtained horizontal displacements from the DINSAR data by the classical trigonometric calculations, considering the displacement direction from ground-based data. For this group of inclinometers, this image here compares the measured direction of movement to the local, to the direction of local maximum slope. You can see that there's a difference. Let's recall that in the literature, frequently displacements are assumed in the direction of the maximum slope, especially at the low and medium scale analysis. What's the consequence of that in different areas of the slope? You can see them from these plots, the black dots, in terms of coefficient of conversion from loss displacement to horizontal displacement by considering either the maximum slope or the measured direction of movement. The dashed one-to-one line would represent no difference. So from this plot, you can see that there is actually a difference. In some cases, significant for this slope where displacements visible by the satellite represent a small component of the total. Why is there a range of lost displacements for a single building? If we look at lost velocities against longitude and latitude, we see almost linear variations, and this suggests two possible mechanisms: either a horizontal deformation of the building or a rotation of the building, in this case around this axis. Both mechanisms could contribute to what is observed from the insert data, but by using the first or the second hypothesis, in this plot respectively in blue and red, some differences are observed in terms of the calculated horizontal displacement rate along the area of the building. Here at the left, I'm comparing ground-based data to DINSAR data in terms of horizontal displacements. A good agreement is found as long as one considers the correct direction of movements. In this plot at the right, I'm showing cases in which DINSAR data helped to improve displacement time series, either by filling the gaps of information for some periods deriving from ground-based data, or helping to extend them forward in time. You can also see here that there is a fundamentally a continuity between MVSAT and Cosmos SkyMed data. DINSAR data, together with all the other data, allowed to detect in many areas of the slope a substantially constancy of average rates from 2005 on. What happens if we also consider Earth's data going back to 1990s? In this period, this is the accumulation of Varkoditso Earth flow. There are some inclinometers, but their monitoring period was quite short. We used them mostly to reconstruct the geometry of the slip surface. If we also use DINSAR data in green, we spot higher displacement rates in this period, which corresponds to shortly after the construction of sheet pile walls protecting the railway here. Afterwards, from 2000 till nowadays, displacement rates resulted slightly lower and almost constant till recent days. Another important thing is that Cosmos SkyMed data allow to improve the knowledge of displacement distribution in space, in particularly by looking at roads, which frequently in sparsely inhabited slopes are the elements, the main element visible by the satellites, and also one of the elements at risk. The national road crosses both earth flows. For this sector, I'm showing lost velocities, and the footprint of the landslide, red data, is quite evident for a stretch of road around 150 meters long. For comparison, I'm also showing as gray dots the data of this other sector crossing the other lower earth flow. As for the red dots, here you can also see the evolution of lost displacements in time. They correspond to horizontal displacements around 1 centimeter per year. This is the zone between the national road and the railway. We are seeing here lost displacements against the distance along the landslide horizontal, the landslide longitudinal axis for time periods around 2 years from each other. These parabolas represent statistical elaboration of data, and here you see a plot of lost displacements against time for 3 points of the parabolas. you see that the maximum of the parabolas is more or less halfway between the national road and the railway, both reinforced by sheet pile walls contrasting landslide displacements. Might this be a distorted image of the real ground displacements? Yes, possibly for two reasons. First, at the center, the shallowest soil horizons might give more contribution to total displacements than the zones closer to the reinforced road and railway. And second, there is this inner local slide related to river toe erosion, which might cause a progressive change of direction from upslope to downslope. By pushing together all the data, inclinometers, GPS, DINSAR, we obtained this field of displacement rates describing the main kinematic features of the slope, and in particular of the two main earth flows, which behave quite differently. This one has a rather continuous variation of displacement rates along its axis. In the channel, displacement rates are an order of magnitude higher than in the accumulation. In the central part of the accumulation, we seem to spot some slightly higher displacement rates, again related to river toe erosion. The other earth flow has more heterogeneous behavior, with an upper zone whose rates are around 1 centimeters per year, a central zone with almost no displacements in the monitoring period, and the lower zone from around here to the river, where displacement rates were from 7 to 1 centimeters per year. Finally, we can look with the help of the insert data to the effects of some remedial measures that were realized in the area by different public subjects, in particular these two encircled areas. At the western sector of the slope, a large landslide affects some buildings and the junction of the national road. These two drainage wells were constructed in the 90s. We don't have the insert data relative to this period, but the data of the last 17 years show almost constant displacement rates in the order of 3 centimeters per year, notwithstanding the construction of the drainage wells carried out in the 90s. Ineffective drainage systems is something that we are finding in several cases in our region, and that might be related, I'm going to conclusion, to
Dr. Vassilo, please,
yes.
let's move to the conclusion.
Okay. Other indication comes in this other area where sheet pile wall was constructed to contrast landslide displacements affecting the national road. And again, the insert data allowed to see a reduction of displacement rates after the construction. Concluding, the long-term monitoring, more than 15 years of the Arco-Clay slope is taking advantage of the integration of different techniques. Notwithstanding the direction of movements unfavorable to the insert monitoring, ground-based results allow to exploit satellite data to extend the displacement information in space and time. All this would have been much harder, if not impossible, without inclinometer measurements. About this latter point, I'm just very rapidly comparing this landslide system that I showed in the presentation to another one that we studied recently in Latronico. The two landslides have practically the same ground displacement rates when compared in terms of the displacement rates along the loss with the same scale of representation. They look completely different. Why is that? Just due to the prevailing displacement direction, which is different, and therefore to the different satellite visibility of displacements. Thank you very much for your attention.
Thank you very much, Dr. Vassilo, for this nice presentation, combining different monitoring methods. Let's move to the next, I suppose that will be pre-recorded video. We'll start.
Hi everyone. In this presentation, I will show you some data depicting the movement of deep-seated landslide by multi-stage creep we recorded at the La Montagna landslide in the Apennine Mountains of southern Italy. Before to see the data and provide some potential interpretation about landslide dynamic and factor controlling movement, let's go through this graph to introduce the topic of landslide movement by creep. So the black curve we see in the graph reported in this slide represents somehow the nonlinear deformational behavior of continuum material subject to what we can define as an approximately constant stress. This behavior is generally consistent with creep in landslide involving cohesive soils. And what we can observe is that under this condition, such material can display three measured kinematic stages. In other words, the three segments of the curve belonging to these three regions of the graph. In the first stage, the initiation of the deformation occurs as a transient increase in deformation rate, and for landslide, this transient acceleration might be related to a transient increase in stress around landslide base, induced, for instance, by a pore pressure increase. After this initial stage, landslide materials commonly keep the form steadily, and this behavior materializes what happened under steady creep condition. Subsequently, an evolution toward an accelerating creep behavior might occur. If this occurs, the deformation rate continuously increases following this pattern, the pattern displayed by the black curve, and slope failure is expected to occur when the FOS equals the unit. This is consistent with the model proposed by Petley and co-authors. This last behavior, that is landslide, is commonly related to the nucleation and development of a shear surface, is not always observed in natural experiment. In fact, some landslides move persistently by viscous flow, while others show attenuating or non-attenuating pattern as a consequence of the ductile nature of the soils involved that might not behave similar to continuum materials. An example is reported in the graph through this dashed line segment. The La Montagna landslide in the Apennine Mountains of southern Italy, object of our analysis, represent an exception in this perspective, since it consistently moved at least in the last 10 years, showing a kinematic consistent with nonlinear creep in continuum material and exhibiting a marked phase of accelerating creep behavior. This landslide developed at the upper edge of the Monte Aguto flow that in this picture is depicted by this red dashed line and represent somehow a result of the upslope progression of the upper boundary of the Monte Aguto flow. In its configuration, the landslide is approximately 400 meters long, 130 meters wide, and has a maximum thickness estimated in 20 meters in the upper part of the landslide. It involves an estimated volume of 300,000 cubic meters of fine-grained flishoid materials. And a comparison between an available pre-landslide leader-derived DEM with a recent UF-based photogrammetric DEM indicated that, as expected, the upper part of the landslide consistently lost material during slope evolution, while the lower part of the slope consistently gained material, and the maximum elevation change due to depletion in the upper part was estimated in 14 meters. A similar elevation change was observed in the lower part of the slope due to material accumulation. Field observation indicated the presence of deformational structures we reported in this map, indicating substantially the overall stretching of the upper part of the landslide, materialized by sets of tension crack and associated normal and oblique faults, and the compression, the shortening of the lower part of the landslide at its toe, materialized by association of truss faults and pressure ridges. Overall, the upper sector of the landslide displayed the characteristic of a translational slide, as we can observe in this upper picture, with association of surface structures consisting in, as we already discussed, tensile crack and normal and oblique folds, while the lower part of the landslide displayed the characteristic of landslide moving by flow substantially, with a flow-like surface morphology and association of compressive structure and a fan-shaped toe. On this basis, the landslide can be considered as a complex landslide, and it developed in a sector of the slope characterized by a specific geologic setting that, in our opinion, control slope evolution. Especially the La Montaña landslide developed in a sector of the slope characterized by the presence of a synform and involves the rocks of the Faetoflish formation. Such rocks consist in an association of limestones with marls and clays, and the presence of multiple clay layers within the succession represent an important predisposing factor, since the basal slip surface of the La Montaña landslide occurs within a few decimeter thick clay layer. In this picture, we have an overview of this singular feature of the La Montaña landslide. Indeed, after the movement, on the left flank of the landslide, an extensive exposure of the basal sliding surface developed. The exposed morphology seems to be somehow consistent with the expected geometry of the eastern flank of the interpreted synform forming the slope in this part of the La Montaña Mound, and the exposed basal sliding surface was formed by a clay-rich material that we can observe in the inset picture, consistently striated. And at the moment of the field inspection, when we took these pictures, such material had a water content around the plastic limit. In September 2018, before the landslide failure, we installed an instrumentation station consisting of an Arduino-based data logging system, a high-resolution wire extensometer, and a rain gauge. The system was powered by a solar system, and these pictures provide an overview of the system and its installation position next to the upper left flank of the landslide. This position was selected because of the need of anchoring the cable of the wire extensometer to the stable ground for displacement monitoring, and for this monitoring station, an Arduino with a built-in Sigfox-based transmission system was used in order to provide real-time data. The monitoring experiment began in September 2018 and ended in November 2018, immediately after slope failure. Monitoring data were acquired with a sampling time of 1 hour. This graph reports results from monitoring station in terms of registered cumulative displacement and derived velocity. In the graph, the black curve represents cumulative displacement and the gray curve represents the derived velocity. So, analyzing results, in the monitoring period, the landslide moved of approximately 17 meters, showing a typical parabolic distribution of strain that mimics the theoretical accelerating creep behavior of continuum material. Considering this observation, velocity data were used to evaluate the potential of the inverse velocity method to predict timing for slope failure. As you can see from the graph, especially the black curve depicting the inverse velocity fit, the predicted failure time was consistent with that observed in the field and represented by the black star along the displacement curve. In order to better understand landslide dynamic, velocity data were used to derive acceleration time series and related virtual force driving movement. Acceleration data showed a sinusoidal time series indicating a well-defined single episode of movement characterized by an initial downslope acceleration of the landslide mass, followed by a consistent deceleration that stopped the moving mass. Before slope failure, the acceleration consistently grew with time, confirming the accelerating creep behavior of the moving mass, and the kinematic, represented by the acceleration time series, was consistent with the time variation of the virtual driving force derived by the estimated momentum and the landslide mass. In order to contextualize acquired data in a long-term slope evolution model, we used multiple imagery, including Google Earth and aerial and UAV-derived orthoimagery, to track long-term displacement of objects identified at the landslide surface into a GIS environment. For this analysis, objects like rocks accumulation, landslide surface structure edges, and boulders were recognized and tracked. This graph reports the long-term displacement evolution of the landslide surface. Also on the long term, the displacement curve derived by the analysis has a shape consistent with that characterizing idealized continuum materials deforming by nonlinear creep. In our case, it is important to notice that we do not fully know the timing for deformation initiation, or in other words, landslide initiation, since the point depicted with the label 0 is only an interpretation related to image variability. We expect that landslide initiation was located from in time between the 0 and the 1 points. Subsequently, starting from the reconstructed displacement history, an evaluation of factors potentially controlling the development of the landslide and its evolution was completed. So in this slide, we have a summary of the first analysis we completed related to the potential influence of slope modification on landslide development. Since landslide involved the upper edge of the Monte Guto flow, we used multiple digital elevation models to understand the potential effect of slope modification induced by the airflow evolution on the La Montagna landslide initiation. So that DEM differencing analysis was completed considering the area depicted by the yellow polygon in the inset map located at the left-hand side of the slide. And results of the analysis in terms of volume change are reported in the graph by the gray line. So this line depicts somehow the variation of the volume related to elevation change in this yellow region of the landslide. It's interesting to note that a consistent volume loss occurred between the points indicated with 0 and 1 when the landslide potentially initiated, so that we cannot exclude that the formation initiation was also related to slope modification induced by the evolution of the Monte Guto earthflow. A further aspect that was analyzed was the potential effect of rainfall events on slope evolution. In this perspective, monthly rainfall data registered at the nearest meteorological station were used to make a comparison with the reconstructed displacement history. The considered meteorological station was that located at Savignano Irpino, 5 to 8 kilometers far from the landslide. It is interesting to note that on one end, between the end of 2008 and the beginning of 2009, a series of above average rain months occurred, potentially contributing to landslide initiation, and on the other end, the apparent transition between the steady state creep and the accelerating creep phase occurred as a consequence of a major storm event that hit the landslide area in October 2015. In other words, this event. So, in conclusion, the La Montagna landslide consistently moved in the monitoring period, and a total displacement of 17 meters was registered by our monitoring system. Slope failure occurred after a period of accelerating creep materialized by a parabolic distribution of strain, and such distribution was consistent with cytolinearity, so that inverse velocity method well predicted the slope failure on November 5, 2018. Monitoring data were used to interpret landslide dynamic to a simplified virtual driving force history reconstruction, and a single cycle sinusoidal-like force pattern was somehow observed and interpreted as consistent with the observed single episode of movement. The long-term displacement pattern was consistent with the expected deformational history for nonlinear continuum materials, and the accelerating creep phase was potentially initiated by a series of rainstorm events associated with slope modification. So I have concluded. Thank you for your attention.
Thank you for this recorded video. Was respected exactly the time, and we will now let's move to the other presentation, which will be the last of the first part, which will be given by Professor Damiano.
Okay, thank you very much.
Thank you. Can start.
I share my presentation. I hope that you can see it. No? Okay, can you see it? Yes. Thank you very much, Mr. Chairman. And good afternoon to everyone. In the next, I'll present you a plan for a quite different type of monitoring system, in particular for an integrated structural and geotechnical early warning system for deep-seated landslide based on a new smart hybrid strain transducer. Okay, Italy, as you know, is a country where landslide risk is very high, and where railway and highway networks frequently intersect unstable slopes with more than 2,500 critical points. Even in the geomorphological context of the stiff clay and flysch formation, the presence of such complex landslide system represents an important geo-risk for the Italian transport system. So to protect and surveil the exposed structures and infrastructures, we need to increase the efficiency level of the existing early warning system, integrating traditional monitoring device with new sensors, with new transducers, able to perform continuous spatial and temporal measurements of both slope movements and their effect on the exposed infrastructures. To this aim, I'll present you a new smart hybrid strain transducers that we have developed at our university in cooperation of these transducers as smart vertical and horizontal inclinometer, and finally how we have tried to explore the possibility to use it in an integrated structural and geotechnical early warning system for complex landslide interacting with infrastructures. The new strength transducers belongs to the distributed optical fiber sensor family, and the sensing principle is based on the well-known Brillouin scattering phenomena, which is induced along an optical fiber and which in turn is related to the fiber strain. The use of optical fiber for strain measurements is becoming popular in various fields of the engineering, of the civil engineering, and also in the field of geotechnical engineering. And this is mainly due to the fact that they can realize a cheap continuous monitoring system with a typical spatial resolution of 1 meter for potential application over distance as long as tens of kilometers, and with the short acquisition and processing data times. So they seem to be very advantageous if compared with conventional point measurements that only provide local information. However, they also suffer for some limits. For example, in many geotechnical applications, the fiber is simply embedded into the soil, into the ground, and this can cause a limited stress transfer between the sensor and the surrounding soil. And this occurs especially at high strain levels. In addition, under natural environmental conditions, the sensor, which is constituted by the optical fiber itself, may suffer for damage. So the novelty of the new strain transducer is that it has been designed to overcome these limits. The sensor is the optical fiber is incorporated into a central resin core, and this core is then packaged between two tapes realized with a composite hybrid materials. We can use different type of composite materials. As an example, we have tested the glass and carbon fiber. This packaging gives to the transducer a flexible structure, and in this way, it is possible to industrially produce transducer even longer than 100 meters. They can be easily rolled around a support for transport, and finally they can be installed on site in both structural and geotechnical application. Here I reported the result of a first test that we have performed to evaluate the effectiveness of the new transducer as a smart vertical inclinometer. In this test, as an example, two new transducers have been fixed along an aluminum pipe used for conventional inclinometer measurements. Then the tube, initially vertical, was deformed, and the comparison between measurement retrieved with a standard inclinometer device and the new transducers was performed. Here, in this diagram, on the right side, I have reported the imposed displacement at the location, at the side of the two transducers. And I want to highlight that relative displacement between the two extremities of the transducers was as high as about 20 centimeters. And this in order to evaluate if a fully stress transfer between the transducer and the pipe realizes even at high strain rates. The results are reported here in terms of strain profiles along the depth. And the green diamonds, the green lines, indicate the profiles obtained by double derivating the measurements retrieved by a vertical inclinometer, whereas the red and the light blue dots indicate the measurements retrieved by the new one. And as you can see, the new transducer, the measurements retrieved with the new transducers, well match in values and trends the conventional ones, revealing the reliability of the new sensors. Similar good agreements have been reached also during another test in which the transducer was used as a smart horizontal inclinometer. Well, on the basis of these quite good experimental results, we have tried to explore the possibility to realize an integrating an integrated structural and geotechnical early warning system based on the use of these new transducers for a complex landslide in clay soils that is the Petacciato landslide that is located here in the Molise region near the Adriatic coastline. This is a very large slope movement that is characterized, as you can see in these two cross-sections, by the presence of multiply sliding surfaces, which depth reach even 100 meters. And this slope movement periodically reactivates after intense rainfall with a short time lag of about some weeks, so not a so long period. And with the, in some cases, the development of new sliding surfaces within the main landslide belt. Unfortunately, the landslide interacts here near the coastline with two infrastructures of main importance for national transport system, and in particular with the railway network that requires an effective surveillance system, as also a few centimeters of relative displacement could cause misalignment of the tracks and potentially the derailment of the trains. Currently, there is a complex monitoring system which is active in the area, which consists in a series of traditional inclinometers indicated here by the red, yellow, and green triangles, in a number of piezometers, and in GPS and displacement sensor for monitoring the infrastructure. Recently, this system was has been integrated with installation of some fixed probes for automatic acquisition. However, as you can imagine, due to the wide extension of the landslide and to its very complex kinematics, which in some cases underwent displacement of tens of decimeters in few days, there is still the need to enhance the monitoring system with cost-effective sensors of higher spatial and time resolution. So, in other words, this seems the typical case in which the system based on the new transducers could greatly enhance the monitoring system already active, already predisposed. In detail, we could think that we can realize a system with the new NSHT transducer consisting in the installation of various peripheral transducers for monitoring at the same time both the slope and the exposed linear infrastructure. As an example, the new transducer could be installed at different points within the slope as a smart inclinometer, but also along the tracks of the railway and along the structural elements of the viaduct as distributed strain sensors. As a smart inclinometer, we could also think to instrument each standard conventional inclinometer using three new transducers fixed along the external surface of the pipe in order to retrieve the vertical strain soil profile even up to very high depth. In this way, the formation of even thin shear bands, wherever they develop, could be detected in early time. when for early time consider that the acquisition time of the system requires only a few minutes. The same result, for example, could not be achieved if even if we install fixed probes, because in the case of activation of new sliding surface, these probes are able to read the movement only if they are located very close to the new sliding surface, with the risk of missing or better of revealing slope movement only in the
Dr. Damiano, please. Dr. Damiano, please, can you conclude?
Yes, of course. So,
please, can you conclude, because time is the time, please.
It's time to go. Okay. So I want only to share only to point the attention that all the sensors can be connected to a unique central data acquisition and transmission unit, so that from a single access point, it will be possible to query the entire network of transducers simultaneously. And this can realize an increase of the efficiency of the early warning system. So, summing up, we can see that the main advantages of implementing this new transducer in an early warning system for this kind of complex lens slide is that first we have the possibility to perform continuous, timely, and standalone monitoring in both structural and geotechnical fields. That when used as a smart inclinometer, the new transducer can individuate in real time the formation of new sliding surfaces wherever they may occur. We can realize also a structural monitoring system for monitoring the strain state of structural elements, and finally, the transducer can be manufactured at very low cost, and in the case of such deep and complex lens slide, its use seems to be particularly advantageous also from an economical point of view. Finally, it's, as we have seen, the sensitivity of the new transducer is at least the same of the traditional one, and it also is able to realize a fully stress transfer between the transducer and the monitored element. Okay, I would acknowledge some people who participate in this research and you for your kind attention. Thank you.
Thank you, Dr. Damiano, for this nice presentation, and interesting presentation. We are now pleased to pass to animate the discussion by the Professor Casagli, and please, you can start.
Okay, thank you very much to
Professor Casagli.
Can you hear me? Thank you very much for your introduction, and thank you to the speaker. They present a very wide view over different monitoring techniques ranging from satellite to borehole in instrumentation. I check if there are questions from in the system. No question. I invite the audience to put the question into the question and answer section. And I have some questions, some points for discussion. Starting with the order with Pierluigi Conforto. You presented a warning system based entirely on remote sensing data on radar satellites, Sentinel-1 satellite. What about false alarms? What is the frequency of false alarms when you detect some acceleration, anomalous acceleration?
Thanks for the interesting question. Actually, there are several points, anomalous points showing false positive. And this is an issue which is taken into account also because of the settings we implemented. Of course, I can show also some of the picture, some of the slides I've shown before. So for instance, we can see in Tuscany, it's let's say less than 50% of the anomalous points can be classified as not determinate or as rumor, so as a noise of the systems. But of course, this can be reduced and can be improved, an aspect that which can be improved, of course. But in this case, we would like also to highlight that interpretation given by the geologist, by SAR expert, is fundamental to address correctly every signal detected. Also in the other region is more or less 50%. Of course, in Valle d'Aosta is a little bit higher due to the settings, to the alpine setting, as well as we have more rumorous points in the alpine setting of the Veneto region. So this also depends on the decorrelation problems which can be experienced in very high settings, such as the high mountains of the Alps.
Okay, thank you very much. And I have a question for Roberto Vassallo.
Yes.
You show an impressive presentation combining remote sensing INSAR data with a large amount of in situ data. And you show that using high-resolution satellites, such as Cosmos SkyMed, it's possible to monitor geotechnical problems such as differential settlement, the effectiveness of engineering works, and also to provide an intra-landslide hazard zonation. And more important, you show that it's possible to have this very accurate monitoring also in difficult condition with slopes oriented north-south, that is the worst orientation for satellite. So I want to ask you, what is your opinion on the integration of remote sensing and in situ data for geotechnical problems?
Well, what I feel, what I tried to show by my presentation, is that integrating different data, so deep measurements and shallow measurements, allows to have a much more detailed picture of movements, of kinematics, and so on. In particular, for the case that I showed, I tried to highlight that by using the geotechnical data, it is also possible to push forward the use of satellite data in difficult conditions. I mean, just a small component of movements visible by satellites means that frequently you would almost exclude those data without a deep knowledge of what is happening underground. This is kind of important because otherwise we run the risk, especially for non-specialists, let's say, to look at distorted images of displacements as loss displacements, and maybe miss some details of the kinematic features of a slope. There are, of course, cases in which the conditions are much more simple. As you were saying, in the case in which the direction of movement is almost parallel to the satellite line of sight. But there are many conditions in which this does not happen. I'm thinking of our region, in which frequently there's a valley with the river running more or less from east to west, and therefore inevitably the slopes being north-south oriented. Thank you for your question.
Okay, thank you very much. And coming to Luigi Guerriero and Giuseppe Ruzza, you show a very interesting application in which you demonstrate how it's possible to derive a lot of information even from a very basic monitoring system like a wire extensometer equipped with a low-cost transmission system. So my question is, what is your opinion on low-cost monitoring on a slide? Not always is possible to do geotechnical campaigns, to drill boreholes, to deploy in situ instrumentation, to use satellites. So the low-cost sensors are very important for many landslides, even in developed countries, but more in less developed countries.
Hi, can you hear me?
Yes, we can hear you, but we cannot see you.
One moment, please. I activate the camera. Okay.
Okay.
Thank you for the question. Yes, the low-cost system opportunity for research for develop a new system for monitoring landslide. We develop also other system such as inclinometer and other system with low cost system. Yes, but this system can have many few limitation respect to the ordinary system for landslide data acquisition. But in this year, such as in my PhD study, I developed an inclinometer and inclinometer for landslide monitoring application, and use also for the compare the data from the low-cost monitoring data, such as the satellite data from such as nanosatellite data. And yes, the low-cost system a great opportunity for science and such as for application in slide monitoring. Thank you.
Thank you very much. And coming to Emilian Damiano, I can say that the dream of every engineering geologist and geotechnical engineer is to replace inclinometers, manual inclinometers, with something much clever in terms of data acquisition, data transmission. And you show a very interesting technology you call smart hybrid transducer, which has the potential to replace inclinometers. But in the scientific literature, we have seen many attempts to replace manual inclinometers, with multi-base automatic inclinometers, with mechanized inclinometers, but inclinometers are still there, manual inclinometers are still there, are not yet replaced. What is the potential of your technology with respect to the others? Damiano is connected or not?
Yes, yes.
Okay. I cannot.
Okay.
Okay, I can see you.
Thank
now.
you very much for your question. Yes, I hope that the dream is not so far now by these new transducers, but I know that inclinometer measurements are one of the most important instruments to understand kinematics of a landslide, and we have a lot of road to reach the dream. But our new application, our new transducer, has the potential to be cheap, as Elias said, but also to perform really a distributed measurement of strain profile at the moment along a depth, along a vertical in the soil. So I think that in the future, if we are able to test this kind of strain transducer in field, and if we are able to couple the strain profile with the inclinometer measurements, as I said, the new transducer can be fixed along a pipe for conventional inclinometer measurements. We can also, in a first time, have a sort of redundant system, so that also we can check the effectiveness of our sensor in reproducing, in measuring the displacement soil profile. We need obviously a time for give these for do this work, but I'm really convinced that in the future we can also reach this objective, that is this aim, that is to try to have a continuous monitoring system which can reveal the formation of new sliding surfaces, and we can catch the slope movement to up to very high depth in the soil. Thank you.
Okay, thank you very much. We have 5 minutes at the end of the session, and we have 60 participants to this session. I ask if some of the participants has question for the speakers. If not, I ask if the speakers want to add some comments, or if the chairman, Professor Jamei.
Sorry, I have only a remark and a question for Damiano. I remember that in the last International Congress in Naples, in landslides, there is some companies who presented some new equipments to follow landslides, to follow as new sensors and optic sensors who can replace the inclinometers. Can you comment this according to your experience and to your development in this field?
Okay. Yes, we have There are some other experiments in the literature by other group of researchers to try to develop a new sensor to have inclinometric measurements. But by now, in my knowledge, most of the experiences are based on a quite different technology, which is the fiber grating, which perform only local measurements. And probably the most difficult thing is to realize a support for the fiber, for the optical fiber, that is not damaged during installation. This is more a technical aspect that we cannot forget. And so the first attempt that had been suffered for this technology, for this limit, technical limit, and also for the type of sensing technique that have been used. I repeat, this is only a first attempt. We have reproduced we have tried to analyze the effectiveness of this sensor with the laboratory tests, but in our application, we have tried to overcome the limit of the technical problems that would arise when we can try to use the optical fiber as a strain sensor.
Thank you. About the optical fibers, I don't know if their use it is more useful for in the earth, in the soil, or if we have, for example, some structure near the landslide zone. What is the better to place it? Can you give some advice about this?
No, I think that it is useful for both soil monitoring and for structure. I know that for building and for structuring infrastructure, optical fiber technology is more advanced. We have many research activities in this application field, more than in geotechnical probably, but I think that it can be a very wide and diffuse technology to be used for both field of applications.
Okay, quickly question for Dr. Confiorto. Please, can you talked about some classification, municipality classification. What is the basic of this classification? Because it is interesting for practical point of view. But is it a standard or is it only locally related to the municipalities?
Both ways. Let's say both ways. Of course, we rely on standard classification. So basically we divide the anomalies between slope instability and subsidence, which are known phenomena. Of course, there are also some local specifications, such as in Tuscany, we classify some anomalies according to the geothermal activity, or we have dump sites which are subsiding. So therefore, according to ancillary data, such as slope, such as aspect, such as DEMs or land cover, we classify specifically some areas and some anomalies, let's say in this way.
Thank you.
Thanks to you.
Thank you. I think it is time now to have the break.
Yes, it's time to leave this session. Many thanks. No, probably it was interrupted. Yes, the connection.
Okay, we can close the session.
Yes, we have to close the session.
Okay.
Many thanks to Professor Jamei and Professor Casagli for their very important and good jobs. And we have to leave this room in order to go to the other one for the next session analysis. The job from Professor Jamei is not finished, you know. So
Yeah.
you will receive another link for the next Zoom. Thanks to the participants.